Okay, we're continuing on here, chapter 4, which we talked about last week, whatever was in that chapter. But I think it had to do with atoms, I believe. And I believe at the beginning there, we talked about some experiments that helped us understand the structure of the atom and sort of the particles that make up the atoms, like protons, electrons, and neutrons. So we talked about Thomson. We talked about Milligan. We talked about Rutherford. We talked about the plum pudding model, which was sort of the early model there of the atom, and obviously not so correct. So the end result was we had an atom that has a nucleus, right? And in the nucleus, we have protons and neutrons that are found, protons being positively charged, neutrons being having no charge. Out in that sort of empty space are electrons, which are negatively charged, traveling in a random pattern around the nucleus. We also talked about a couple other important aspects of atoms, which was the atomic number, which is sometimes the number of not neutrons, protons would be good. Number of protons there are in an atom. Remember, the atomic number can be found on the periodic table. It is that number there above the symbol is the atomic number. Also, that every atom has, or every element has its own atomic number or number of protons. And it really is the number of protons that's most important in terms of what element you're talking about. So if you know the atomic number or the number of protons, which again is the same thing, and you have a periodic table, you should know exactly what element you're talking about, as everybody has their own atomic number. Mass number, which is our number of protons plus our number of neutrons. That, again, a reminder, is not found on the periodic table. When you calculate those things like we talked about for protons, electrons, neutrons, they all need to be numbers. Well, we use the symbol for the element, put the mass number up on top, and the atomic number there on the bottom left. And remember that if you subtract the mass number from the atomic number, if you subtract those two, that gives you your number of neutrons, right? So if you take the mass number minus the atomic number, that will get you your number of neutrons. We did eventually talk about the number on the bottom, which is the atomic mass, right? And the atomic mass is based off of all the naturally occurring isotopes for a particular element. And we talked about actually how to calculate that in AMU. You take the percentage of the first isotope times the atomic mass of the first isotope. And then you add it to the percentage of the second isotope times the atomic mass of your second isotope. And however many naturally occurring isotopes, you basically just keep repeating that pattern. And that, again, is how we get to those numbers that are on the bottom. That's also why we talked about carbon-12 was used as the standard isotope to figure out atomic mass. It has a mass of 12, but we do see 12.01 for carbon. And that's because carbon naturally has a mixture of both the carbon-12 isotope and the carbon-13 isotope. And the average value for those guys is what we actually do see on the periodic table there. We also talked about the periodic table itself, I believe. So we talked about the periodic table. Remember that groups 1, 2, skip the middle, 3, 4, 5, 6, 7, 8. Groups go up and down, right? Periods go left to right, and there's 7 different ones. And some of these groups do have some important names. Group 1, which does start with lithium, is our alkali metals. Group 2 is our alkaline earth metals. Group 7 is our halogens. And group 8 is our noble gases. Also, between group number 2 and group number 3, we have our transition metals, right, down there. And these are our lanthanide and actinide series, which, if you follow the atomic numbers, should go right about there in terms of where they should be. We then talked about at the very, very end the electromagnetic radiation. And the idea, what we're talking about in this chapter, the rest of this chapter, is the idea of electrons and sort of where they are in the atom. And as they transition from one energy level to the next, they do have to give off a certain amount of energy. For example, if they go from a higher energy level to a lower energy level, that energy, remember, comes off in the form of a wave. And there's a relationship between the wave and the energy associated with it. And if we take a look at a wave that looks something like this, it has a pretty long wavelength, which is what lambda stands for. So that's the wavelength. It also has a lower frequency. And those type of waves typically have lower energy. And that's different than a wave where we have a much smaller wavelength. We have a higher frequency. It occurs more often, and that usually means higher energy, right? And depending on sort of where that wave comes off of in terms of its wavelength, might be in different parts of this electromagnetic spectrum. So for example, here, if we look at this is a longer wavelength on this side, which means it's lower in energy. And over here, this is a much shorter wavelength, which means it is higher in energy, right? And on the sort of far side there with the longer wavelength, we have things like radio waves, which, again, as I talked about, I think probably last time, we tune our radio into a certain frequency, right? And that is basically what we do when we tune it in there. It has not a tremendous amount of energy, but it does have some energy associated with it. Next, we have microwaves, which the wavelength is getting smaller and has a little bit more energy. And again, it has enough energy really to spin water molecules, as I mentioned last time, pretty quickly. And then your food cooks pretty fast in that sense. We have infrared, which is really where we kind of feel heat and that type of stuff coming off, a much smaller wavelength. And here in the visible part of the spectrum, which is right here, this is where we see colors. This is sort of that Roy G. Biv type of deal: red, orange, yellow, green, blue, indigo, violet. And that is where we actually will see colors. So kind of like I think we might have talked about as well, like fireworks. When you shoot off fireworks, they explode. The elements that are there, all the electrons get really excited from the energy. They come back down to a lower state of energy. They release that, and they release waves in the form of visible light, where we can see colors. And I think we talked about, maybe you've done like a flame test by accident by your cooked pasta water, and it overboils and it hits the flame. If you have, again, a sort of gas cooked up, and your flame sort of changes color for a second when the water hits it, and that's really the sodium ions, for example, getting excited, and you'll see really that color of sodium that happens. Now, even with colors of light, there is differences in terms of the energy. So red is a longer wavelength, which means it's going to be lower in energy than over here at the violet side, which has a shorter wavelength and be higher in energy. So even between colors, red, orange, yellow, green, blue, indigo, and violet, there is a difference in terms of the energy associated with those colors that you see. So what does that really mean? It means that maybe in the case of violet, and you see something that turns out sort of that color, you're seeing an electron transition, a lot of energy levels, which would require a lot of energy to be given off by the atom to do so. Maybe you see a red color, which means maybe that electron just dropped like one energy level, not a big transition in energy, didn't give off a big amount of energy, and that will correspond to a red light. Continuing on, much shorter wavelength at ultraviolet. Again, why we put sunblock on, not so good to be exposed to that. It's good in certain places, but not so good in other places. X-rays, as we might have talked about, right? Lead vests, they leave the room when they shoot you with those X-rays. And gamma rays, as we might have talked about when we did some of those experiments. or talked about those experiments, that's really just a pure radiation, radioactive sort of ray, and very, very high in energy. You use something that's a gamma emitter, you have to use a lot of protection so that you do not radiate yourself a lot when you're using it. So this is the electromagnetic spectrum. You do need to know it in the sense of which one would be, say, higher in energy, which one would be lower in energy, longer wavelength, shorter wavelength. You don't need to know like exact numbers per se, but you would need to maybe be able to put it in order. That includes the actual colors. You put them in order in terms of energy, wavelength, and that type of stuff. Any questions on that? Or anything else we talked about, I guess, is one way. All right. So let's do some of that. Take a second here, identify each of these and which one should have the greater energy. So take a moment and decide. So once again, the relationship you just want to think about is short wavelength, high energy, longer wavelength, lower energy. So when we talk about the colors, again, that's your Roy G. Biv, right? Coming across how it was on that picture. Remember, red is longer wavelength, right? So lower energy at this end, higher energy at this end, as it has a smaller wavelength. That means between blue and yellow, that's blue over here, that is yellow. Blue has a shorter wavelength, right? Which means it should have a higher energy. So I'm gonna go with blue there as the winner on that one. Ultraviolet, infrared, that is ultraviolet, as that is after the visible part of the spectrum, and infrared goes into the visible part of the spectrum, which means it would be shorter wavelength. And X-rays there. Well, we don't use X-rays to cook our food, we use microwaves, right? So not as bad. So X-rays would have a lot higher energy in that case. Any questions on that? So when we talk about electrons transitioning from one energy to the level to the next, it is what is sometimes referred to as quantized energy. And what does quantized energy really mean? It means that essentially atoms will have their electrons move from one energy level to the next sort of completely. And what that means is they will either gain enough energy or lose enough energy to make the transition from one energy level to the next completely without stopping in the middle. So for example, if these lines represent energy levels, if we had an electron here, it would lose enough energy to completely get down, for example, to that energy level on the bottom. It won't stop halfway between. So you can kind of think about quantized energy as like stairs, right? So when you walk stairs, we usually have enough energy to be on this step, right? This step, this step. Even as you go down, you end up on one step or the other. You don't go halfway up a step and decide, I'm going to take a break at this point here and just rest for a bit because you're going to fall, right? And that's how electrons and atoms basically transition from one energy level to the next. They will gain enough energy to fully transition, or they will lose enough energy to fully transition. They will not find themselves in one place kind of in between. And the result of that is if you look at something like an atom through a electron discharge tube, and you light up an element, a lamp of it, like a neon lamp or something like that, the electrical current is going to excite all the electrons in there. And if you look at it through a prism, it'll separate out the light, and what you will see is what is referred to as a line spectrum. And it is a line spectrum because we get distinct lines that occur at specific wavelengths, and they have specific colors. And that is very common in what happens with elements as they are excited and they release energy and relax back down. That is different than, say, something like the sun, which gives off like a continuous spectrum. What that means is instead of the staircase example, you could think of it like a ramp, right? If you're walking up a ramp, you could lay up anywhere you like on that ramp, right? You could stop anywhere, you'll be fine, no big deal. Everything comes off at once. And that's sort of what happens. For example, if you took a spectroscope like in this picture and you looked at something not directly at the sun, but you looked at something that was lit up by the sun, the light, don't ever look directly at the sun, you would see more like a rainbow effect, everything coming off at once, not these really distinct lines that come off when atoms have electrons that basically transition. And that is basically when we think about energy in our electrons, that is where it happens with electrons in these atoms. They go from one energy level to the next. So let's talk about what these energy levels are. They are sometimes referred to as the principal quantum number, or N. The principal quantum number is a fancy name for the energy level, basically. The principal quantum number can have values of N is 1 through 7, basically. So you could have 7 different energy levels at which you can find electrons housed. The N equals 1 level is what is sometimes referred to as the ground state. It is the lowest in energy. It is closest to the nucleus. Anything above that, like N equals 2, N equals 3, N equals 4, and so forth, those are what are referred to as excited states. And those are higher in energy, further away from the nucleus. So these energy levels are where we find electrons within an atom. And within these energy levels, these electrons will be found in certain what are referred to as orbitals. And these are sort of areas within the atom where electrons are basically housed. And that's, again, the idea of quantized energy is a sort of staircase sort of approach. So the idea here is, say, on the first energy level, there will be somewhere where we'll have electrons housed. Then on the next energy level, we'll have more electrons. Next energy level, so forth, we'll have more electrons. Electrons go into the atom essentially always lowest energy to highest. So that is how electrons basically fill the atom. They fill up like the ground floor, and once that's filled, they go to the next floor, almost like a hotel. Well, next floor, next floor, next floor. It continues from the lowest energy to the highest until basically they have a place to put all of their electrons in. And as we talked about, I think last time, as electrons transition from a lower energy to a higher energy, energy has to be absorbed. So if you have an electron on the N equals 1 level, and it gets excited to the N equals 3 level, the atom has to absorb energy. Energy has to be absorbed by the atom. And this would be like if you took a flame test and put the thing in the flame, or you run electrical current, you're exciting the atom, it's absorbing all that energy, the electrons gain the energy and they go to a higher energy level. As electrons go from a higher energy level to a lower energy level, they have to emit energy. So energy has to be given off by the atom. There's the law of conservation of energy, which means if it gains a certain amount of energy, it will then have to lose the same amount of energy to allow those electrons to come back down to different energy levels. So sometimes when we look at spectrums, some are emission spectrum, which is commonly what we look at is emission spectrums. What we're looking at is what's happening as the electrons come back down in energy and giving off that energy in the form of light. But you can, with certain equipment, look at the absorption spectrum, which is what happens when they actually gain energy and electrons go to higher energy level. But most of the time we do look at sort of that emission spectrum. So if we look at these examples here, we want to know, is it absorbed, is it emitted, or is there no change? We have an electron that goes from the first energy level to the third. What happens with energy in that case? It is absorbed. It's going from a lower energy to a higher energy, right? The only way to do that is it has to gain some energy and it's absorbed. Electron goes from the third energy to the second, that is emitted, right? The atom has to give off that energy to allow the electron to drop down to the next energy level. Electron just flying around on the third energy level. No change, just basically staying at the same energy level. So there's really no overall change. It just has this normal energy as it's flying around. Any question on those there? All right, so as I mentioned before, these energy levels are where we find electrons. And again, they're either in lowest energy level or an excited state, which is anything above the first state. And where are electrons found? They are found, and as we talked about, I think earlier in this chapter, electrons do not travel in pretty circles. They travel pretty randomly about, and something again known as the Heisenberg uncertainty principle says the more you know about how a particle like an electron is moving, the less you know about exactly where it's at, and vice versa. The more you know about the location of a particle like an electron, the less you know about how it's moving. And what that was really important is you probably have seen previously, or maybe pretty orbits. And this idea of electrons in orbits was a guy named Bohr and his model of the hydrogen atom. And he had this sort of planetary model of how electrons were. They're in these restricted orbits where they just go in these nice pretty circles around the nucleus. And it really doesn't work that way. A lot of that sort of experiments, things like Heisenberg, things like a guy named de Broglie and a guy named Schrodinger said, works really well, Bohr's model for hydrogen. But unfortunately, hydrogen only has one electron. So as you move away from anything that has more than one electron, it doesn't really hold up his theory. So we move away from Bohr's model of we know for sure electrons are in these orbits going around in pretty circles to this more idea of probability and the idea of, well, I'm not really sure where the electron is exactly at any point in time, but I do know there's a pretty high probability that I could find an electron in a certain location within the atom. And most likely there would be a pretty high probability of finding an electron near the nucleus, right? Nucleus is positively charged, electrons are negatively charged, so there's going to be some attraction there. So near the nucleus should be a pretty good probability that at some point there should be an electron there. As you move away from the nucleus further out, the probability is going to go probably down a lot, right? Because it's farther away from the nucleus. Doesn't mean you can't find an electron out there. Just means that there's probably a lower probability. So really what these things are, which are orbitals, they're basically fancy probability maps, kind of all based on math that nobody wants to do. If you ever take physical chemistry, you do that math, but you don't want to do it. But they're really probability maps of where we find electrons within the atom. Will you actually see like a circle, a figure eight and all that? Probably not. But these again are really just these kind of probability maps of where you could find an electron within an atom. So we move away from Bohr's idea of orbits to this idea that electrons are moving pretty randomly about the nucleus, and they're in what we call orbitals. And a couple of important things about orbitals is any individual orbital can hold a maximum of 2 electrons. So any individual orbital that you have could hold a maximum of 2 electrons. There are different types of orbitals. There are s orbitals. These are the types here. And as you can see, the s orbital is basically a sphere. How many of these orbitals are there? Well, for s's, there's only one. No, there's only one s orbital. So the one means that there's only one type of s orbital, no matter where you find it on any energy level, just one of them, which means if I maxed out the number of electrons I could put in that s orbital, how many electrons could I put in there? 2, right? If there's only one orbital possible, he's going to hang on to basically 2 electrons in there, if those arrows represent electrons, for example. Now, p orbitals look a little different. These are figure eights. And there's actually 3 different types of p orbitals. There is what is referred to as the px orbital, py orbital, and pz orbital. What does that mean? It's like in math, right? There's an X, Y, and Z sort of plane on a coordinate. And that's just how they're hanging out in three-dimensional space. One's on the X, one's on the Y, and one's on the Z. You can envision that the nucleus would be like about there. So probably the highest probability of finding an electron would be in that area of those orbitals near the nucleus. Now, since there's actually 3 different types of p orbitals, if I max out all of them on an energy level, how many total can I put in there electrons? I could put 6, 2 in each. Yeah. If these arrows represent electrons. Now, d orbitals is another type of orbital that we find, and there's actually 5 different d orbitals. And if there are 5 different d orbitals, I'll just represent it with the 5 little dashes. If I filled up all those individual orbitals with electrons, how many could I total put in there? 10, right? 5 times 2 is 10. And that would be 2 in each of these guys. And lastly, there are f orbitals, which kind of looks like a couple of d orbitals together. And there's actually 7 different types of d orbitals. And I'll just draw 7 little lines, 3, 4, 5, 6, 7. And if I filled up all 7 of those with electrons, I could fill up 14 electrons in the d orbitals. Obviously, again, 2 in each of these little lines, if they represent individual orbitals, is where you would put these. Now, let's talk a little bit about some terminology. A grouping of orbitals on the same energy level where there's more than one. Like in this case, right? There are 3 different p orbitals. There are 5 different d orbitals. There are 7 different f orbitals. All of those orbitals together on a particular energy level is sometimes referred to as a subshell or sublevel, depending on your book. Yeah. So this grouping of p orbitals here is known as the p subshell or p sublevel, all 3 of them together. This grouping of 5 d orbitals would be known as the d subshell or sublevel. This grouping of 7 f orbitals would be known as the f subshell or sublevel. We usually don't use that terminology for s because there's just one. So there's just one orbital. We just refer to it as an s orbital. Any questions on that so far? So on these different energy levels, we will find these orbitals. And within these orbitals, we will find the electrons that are there within the atom. And again, here are these sort of probability maps. In the s orbital, high probability near the center. As I mentioned before, sort of over here would be a higher probability of finding those electrons. Here's our p orbitals. And as I mentioned before, as you can see, X, Y, and Z is sort of their orientation. They look like a figure 8s basically, or teardrops. All right. So let's talk about where we find these orbitals here and on what energy level. Starting on the very first energy level, n equals 1, we have a 1s orbital. The first one here means it's on the first energy level. The s means it's a s orbital. That is the only orbital that we have on the first energy level. On the second energy level, we also have an s orbital, but it is known as a 2s orbital. The 2 means it's on the second energy level. It's still the sphere, it's just a little bit bigger. And it's on the second energy level where we first start to see p orbitals appear. And we have a 2p subshell starts to appear on the second energy level. On the third energy level, we also have an s orbital, which is known as a 3s orbital because it's on the third energy level. We also have p orbitals because they started on the second energy level, and that would be our 3 p orbitals. And it's on the third energy level that we start to see the very first appearance of our d orbitals, which is a 3d orbital. And again, each of those lines would represent an individual orbital in this case. And when we get to the fourth energy level, which I'll go higher, just not to write in the middle of that writing there, we still have s orbitals. So we have a 4s orbital. We also still have p orbitals, which is the 4p orbital. We also still have d orbitals, which is a 4d orbital. And it's on the fourth energy level where we first start to see our friends, the f orbitals, appear. And that is where we get the appearance of the f orbitals to occur. So this is also something to keep in mind because it'll be helpful in just a bit. First energy level, only have s orbitals. It is not until the second energy level that you get your p's, not till the third energy level that we get d's, and not to the fourth energy level that we get our f's first start to appear. So again, electrons are going to go in here one at a time, and they're going to fill based on lowest energy. If they're filled, then they'll go to the next, then they'll go to the next until they this pattern until they basically fill all the electrons that need to be filled. So we talked a little bit about some terminology of subshell and sublevel. There's also the terminology that you hear, which is level or shell. And that is an entire energy level, like the n equals 2, n equals 3 level, and so forth. So for example, if I want to know how many electrons would be needed to fill the n equals 2 shell or level, and I want to know also how many electrons needed to fill the 3p subshell or sublevel, and I want to know how many electrons to fill a 4f orbital. So take a moment and decide how many electrons could you do for each of those things. So let's take a look and see. We'll start with how many electrons needed to fill the n equals 2 shell or level. How many total? So n equals 2 is here. The shell or level means every single orbital that's on that energy level. So that is 2, 4, 6, and 8. Yeah, if you fill them all up. How about how many electrons to fill the 3p subshell or sublevel? How many would that be? 3p subshell would be just these guys right here, right? That's those 3p orbitals together. What's that? You do not, because it's specifically asking about the 3p subshell, which is the grouping of the p orbitals together on the third energy level. No, so this question is asking how many is needed to fill up the 3p subshell itself. Yeah, so that would be just those 3 orbitals, which would be 2, 4, and 6. I did not fill those in correctly, but that's eventually 6 would be there. Now, how many electrons to fill a 4f orbital? That is the trick question because it says orbital. It actually would be 2 because it could be this orbital, that orbital, that one, that one, that one, or that one, right? If it asks you how many electrons for the 4f subshell, what would that one be? That would be 14. That would be all of those guys together. So if you're talking about subshell, that's everybody. If you're talking about any individual orbital, the labs like to put that in that question, I think. It's any individual one that is there. Any questions on the terminologies you sometimes hear? It is 2 every time. If it specifically says, 3s orbital, 4p orbital, 5f orbital, it should all be 2. Level is every single individual orbital on an energy level. Subshell or sublevel is basically a specific grouping of either p orbitals together on an energy level, d orbitals, or f orbitals together, which would be either 6, 10, or 14, depending on which one you're talking about. Other questions? Okay. All right. So as I mentioned before, this is how the energy levels look like when we have just one electron in hydrogen. N equals 1. This would be N equals 2, N equals 3, N equals 4. And what we see here is in the presence of just hydrogen, everybody's equal in energy. And what I mean by that is everybody on the second energy level, all the orbitals are exactly equal in energy. Everybody on the third energy level, they're all equal in energy. But when we get more electrons involved, we have some shifting that occurs. And that's because electrons are negative, and you put more electrons together, they're also negative. Do they really want to be near each other? Not really. So that causes a lot of shifting that occurs within the energy of these orbitals. And that's what happens when we get lots of electrons that basically happen. Everybody's not perfectly equal in terms of their energy. And that really does affect how electrons go into the atom, for example. We would go here first, then we would go here. That's the next lowest. We would go here. And by the way, they go in one at a time, and then they actually go back and fill up in a subshell. So they actually go in one at a time and actually come back and then fill. We go here next. There's going to go in one at a time and then come back and fill. And this is the major difference. After we go to 3p, the next lowest in energy is actually the 4s. So they actually get the electrons first. Then the 3d gets the electrons. Also one at a time, and then comes back and fills in the opposite direction. And that happens here, the 5s before the d. And that's an important order in terms of electron configuration. That difference in sort of those things, they do not go in order. So we do want to write electron configuration in terms of filling order. The good news is you could use that, or you could use this. This is something that you could recreate yourself really quickly. So let me tell you how this works. First off, if you know this, and you know what we talked about a second ago, that if I max out the s orbital, how many electrons? If I max out the p subshell, it is 6, right? It's a subshell. If I max out the d subshell, there's 5 of them, which means if I max out the f subshell, there's 7 of them, which is 14. If you know this and you know this is the order at which electrons go in. You start up here always, you go this way, fill, and then you come back this way, fill, come back this way, fill, and you just continue that pattern until you put in enough electrons that you need. So how can you recreate this for yourself really easily? You remember when I said it was kind of important to know on each energy level, what energy level each orbital starts at? S's start on what energy level? 1. So you write 1s. P's don't start until you get to 2. So you just go down to the right of that and put 2p, or 2 there. And D's don't start till, there you go down to the right there, put a 3. And F's don't start till 4th. Now all you have to do is just fill in the numbers underneath. Yeah, so you go like 1s, 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, 4f, 5f, and boom, you could recreate it by yourself by just remembering basically this. And then all you have to do is just fill in the numbers underneath. So if you know this and you know that, you should be able to write any electron configuration that you would need to do in this class outside this class as well, maybe. I don't know where you're doing these things. Maybe you're watching Jeopardy and there's an electron configuration. I don't know. So let us do that. Let us talk about writing proper electron configuration, which maybe your lab manual doesn't really do, but we're going to write it the correct way here in this class. So electron configuration is basically how the electrons are distributed in the atom, what orbitals we find them in, what energy level they're in. Again, they always go from lowest energy to highest. And remember that the number of electrons in a neutral atom will equal the atomic number, right? Because it has to equal each other, positive guys, protons, and negative guys, electrons. We write the electron configuration like everybody else does usually, which is known as the filling order, which is that order that we just saw on the previous page. So let us do it, huh? All right. Let me pop this in here again showing you all you have to do is go 1s, down to the right there, 2p, down to the right, 3d, down to the right, 4f. And again, just fill in the numbers here. So 2s, 2, learn how to count. It would be good too, I suppose. That might be helpful. There you go. All right, 3s, there we go. 4s, 5s, 6s, 7s, 3p, 4p, 5p, 6p, 7p, 4d, 5d, 6d, and 5f. There we go. All right. So now that we got our order here, we also already know our hopefully 2, 6, 10, and 14. We're going to start with good old number 1, which is hydrogen on the periodic table. Hydrogen has an atomic number 1, which means it has 1 proton and should have 1 electron, right? So once again, we always start up here. And we're going to follow these arrows. And so forth, that'll take us through. All right, so starting here with 1 electron, it would be 1s1. That is how you say it, by the way. 1s1 is the electron configuration for hydrogen. The first number is that principal quantum number. That is the energy level. Is that principal quantum number, that N guy. The S is the orbital or subshell the electron is in. And the 1 on top is how many electrons there are in that orbital or subshell. So the information here gives us a lot of information. This tells me I'm on the first energy level, I'm in the s orbital, and I got 1 electron hanging out in there, basically. Yeah. Any question on that? That is also how you should write it. Again, you should write it just like that, superscript there for the electron on top. No dashes, no commas, no weird things people like to do, big numbers in between. It should look exactly like that, by the way. All right, let's continue on. Number 2, helium. Yeah, helium has 2 electrons. Once again, we always start here. So we're going to go to this guy, and this is going to be 1s2. Can I put any more electrons in that s orbital? I cannot, because it's filled, right? It can only hold 2. That means if I have more electrons, I need to continue down my chart there, right? Means the same thing. This is the first energy level. That is the orbital it's in. And in that orbital, there are 2 electrons hanging out and having a nice day. Yeah. So let's continue on to number 3, which is lithium. Lithium is 3 electrons. Again, we're going to start up here. So that's going to be 1s2. I now need to zigzag back and come to here next. And that means it's going to be 2s1, right? If I count up the top numbers, 2 and 1 is 3, which is the 3 electrons that lithium has. Again, this has 1 electron, 2 electrons, 3 electrons. Now, How many electrons does lithium have on the first energy level? 2. How many does it have on the second energy level? 1, right? So we got to the second energy level, and we are now filling that one up. How many more electrons can I put in the 2s orbital? Only one more, right? Again, and that's going to fill it up at that point. Might as well fill it up. Let's go to number 4, which is beryllium. Again, we start at the very top always with 1s2. We then zigzag back here to 2s2. If you count up the top numbers, 2 and 2 is 4. We've now placed all 4 of our electrons. Can I put any more in that 2s one? Where do I need to go next after that? Yeah, I need to go to the 2p, right? I need to zigzag back over here when I'm done there. This means that we now have 2 electrons on the first energy level, right? And we have 2 electrons on the second energy level, right? And that's what these first numbers mean, the energy levels, right? And again, one is closest to the nucleus and lowest in energy. So let's continue on. Number 5 is boron. Number 5 here, boron. Starting at the top, we're going to go 1s2, zigzagging back here, 2s. I know the head is going faster than the hand. I know. Let's try that again. That's just a weird looking ass. So that's what that was going to be. 2s2, and now we need to zig back here to our 2p1, right? And if we count up the top numbers, 2, 2, and 1 is 5 electrons. That means that boron has how many electrons on the first energy level? How many on the second? I heard 2 and 3. The right answer is? It is 3. Yeah. That is the second energy level has 2, and also second energy level has 1. So we have 3 electrons. 2 of them are hanging out in the s orbital. 1 of them is hanging out in the p subshell, right? How many more electrons can I put into that p subshell before it is filled? How many more? 5. Yeah, so 5 more. So let's continue on, which will go to number 6, which is carbon. Carbon would again, starting up the top, 1s2, going down to our 2s, 2s2, 2p2. At this point, if we count up the top numbers, we got 2, 4, 6. Who do we appreciate, right? That is 6 electrons total. We now have how many electrons on the second energy level? We do have 4, 2 in an s orbital and 2 in the p orbital at this point. Continuing on, might as well knock out the first 10 here. 7, which is nitrogen. Should be 1s2, right? 2s2, 2p3 at this point, right? And at this point, we now have 5 electrons in the second energy level. Just for visual purposes, if you look at just the second energy level there and our orbitals, this is really how the electrons are distributed at this point. We have 2 there. And as I mentioned before, in the subshell, they will actually be filled one at a time. They will actually now come back up and pair off, going in the opposite direction. That makes us see that we still have room for 1, 2, and 3 more in that subshell, right, before it gets filled. So let's continue on to number 8, which is oxygen. Oxygen should be, again, always starting at the top. 1s2, 2s2, 2p, bless you, 4 there. We now have 6 electrons on the second energy level, 2 on the first. Number 9 is fluorine, which again, starting at the top, should be 1s2, 2s2, 2p5. And finally here, 10, which is neon here. 1s2, 2s2, 2p6. I have now filled up, if we go look at our little diagram here, I have filled this up, and now this guy is filled, right? And if I had to have more electrons at this point, where am I going next? To the 3s, right? Question on that. That is the way you should write electron configuration. You should not just do numbers. like 2, 8, weirdness that I've never seen other than maybe your lab manual once. Any questions on that? All right, so I did a few. Why don't you do some? Why don't you do why don't you do our friend here? Let's do potassium, which is 19. Why don't you do iron, which is 26? And why don't you do sulfur, which is 16? All right, so take a few moments, write the electron configuration for each of those and see what you come up with. Okay, let's take a look, see how you're doing. So again, the chart which you should learn how to make for yourself will not be provided for you. So again, something you can make pretty easily. We always start at the top and kind of work our way around. So 19, that means we should start up here. That means we need a 1s2, a 2s2, a 2p6 as we come through here. We then will go to a 3s2. If I'm not sure, I could count the top numbers as 2, 4, 10, 12 electrons. So I need to keep going. After that, we're going to zigzag back here to 3p, which could hold 6. And that is 18 electrons, pretty close, I think. And that means I need to go one more. Remember, it is the 4 that comes next. So that's going to be a 4s1 in this case. Yeah. Any questions on that there? Again, no dashes, no commas, no weird things. That should look like that. Any questions on that one? By the way, the highest energy level here is? Yeah, and it'd have 1 electron on that one, right? All right, 26 is, I would say, most of that there. So 1s2, 2s2, 2p6, 3s2, 3p6. We do need to fill that up with 4s2. At this point, we are at 19, I think. 20, that sounds like 19, but one more, I suppose. So that is 20. And now we're going to come back here to our D at this point, and we need 26. So that would be 3d6 in this case. So remember that it is the S, the 4s, and we come back to the 3d, and that is the proper order. It is incorrect if you write 3d6 4s2. Yeah. Because we are doing it based on filling order, and this is the proper filling order. Will you see it the other way? You might, and that's based on energy, which nobody does in chemistry classes. So you should do it based on how we do it. Yeah.
What would you say is the highest energy level for that?
It would still actually be, and we'll talk maybe a little bit about it, but it actually will still be the 4s in that case. It would be. There's actually a change in energy that occurs when you start putting electrons in the d orbitals. So when they go into the atom, the 4s is actually lower than the 3d, so it gets the electrons first. But actually what happens when you start putting electrons into that 3d, they actually switch in energy, and it ends up that the 4s actually, after they get filled, ends up actually being higher in energy in that case. And that also affects, for example, when it loses electrons, which electrons go first. It's the s's in that case. All right, 16 there would be a little bit of what we did there. 1s2, 2s2, 2p6, that's 10, 12, and 16 right there at 4. And lastly, argon is 18, 1s2, 2s2, 2p6, 3s2, 3p6, which is 18. Any questions on those electron configuration? Now, when we look at the electron configuration, for example, for potassium up through here, that is the same electron configuration as who? Argon, yeah? Frankly, if we look at iron as well, we got that going on, right? So we could actually write a shorthand for electron configuration where we could, for each of those, go in brackets argon, which means argon's electron configuration, and just continue on and do a shorthand for that guy. You could also do it for iron, which would be argon 4s2 3d6. Argon is what type of element? It is a noble gas, and that's what has to go into the bracket. It has to be a noble gas, sometimes referred to as noble gas configuration. So for example, if I had sodium, which is 1s2, 2s2, 2p6, 3s1, if I just look at this part of the configuration, that's how many electrons? Is 10. Who on the periodic table is 10? Neon, which is a noble gas. So you could write neon in brackets and just finish out the configuration in a shorthand way. So that's sort of a shorthand. It has to be the noble gas that comes right before the element you're writing the electron configuration for, and you could kind of continue on. Any questions on that there? Those shorthand actions, good stuff. I like it. Question on electron configuration. Yeah. They'll probably just say write the electron configuration. I'll probably take either way as long as it's correct. But if it says do not use the shorthand, don't use it. But if it just says write it, you could write it either way as long as you do it correctly, I think. Other questions? Let's see here. That's a lot of blank pages. When we look at the periodic table, there are certain blocks on the periodic table, and the first two columns are the S block, because frankly, there's how many electrons in the S orbital that you can put? 1 and 2. Yes. The P block on the periodic table is group 3 through 8. If you fill up a P subshell, how many electrons? 6. 1, 2, 3, 4, 5, and 6. Yeah. The D block is your transition metals. If you fill up a D subshell, how many electrons? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Yeah. F block is 14. That's these two rows on the bottom. I won't count them, but there's 14 across in case you don't trust me if you count the squares. You could actually use the periodic table and the period number, the 1, the 2, the 3. And you could actually count off electron configuration if you wanted to. We just did sodium, right? Which was 1s2, 2s2, 2p6, 3s1. Starting up here, this would be 1s1 to 1s2 where helium is. Coming back over here, 2s2, 2p6, 3s. If I wanted to do sulfur, which we also did, right? 1s2 to helium, 2s2, 2p6, 3s2, 3p, 1, 2, 3, and 4. Yeah. You need to be careful. Let's do iron that we did as well, right? 1s2 to helium, 2s2, 2p6 to neon, 3s2, 3p6, 4s2. That's a D, yeah? What D is that? It's a 3D, not a 4, even though it's on 4, right? It's one behind. That is 3D, 4D, 5D, yeah? By the way, if you know that, you can then count correctly. 3D, 1, 2, 3, 4, 5, and 6, yeah? These are to go here, right? That is 4F and 5F down here on the bottom. Gets a little crazy in this area. I would personally not recommend doing that unless you are very confident in what you're doing. You use it to check yourself. If it's something on the outside, you'll be good. But you got to remember 3 is 1 behind the period number. And actually down here, they are actually 2 behind the period number, since they should go over here at 6, and that's really 4. So there's a few places that can get a little hairy, but you can use the periodic table to count off electron configuration if you want to, yeah? Any questions on how to do that there? Fun with the periodic table. I like it. All right, so we did this basically. All right. I'll put it up there in case you want to look at it, but it's basically what we just did on the other slide. All right, so before we move off of electron configuration, any questions on electron configuration? Let's also talk about what happens when we get some charges that happen. Let's say we have oxygen, which we did earlier, and we write the electron configuration of 1s2, 2s2, 2p, and I'm not sure, I'm going to count. 1, 2, 3, 4. That sounds good. 2p4 there, right? Let's say we have oxygen that has a -2 charge. How many electrons does it have? Negative means it lost or gained electrons. How many did it gain? Yeah, so it should have, which means you need to adjust the electron configuration, right? It would be 1s2, 2s2, 2p6, right? It gained those 2 electrons. Let's do our friend sodium that we also did earlier, which was 11. 1s2, 2s2, 2p6, 3s1. Sodium gains a +1 charge. How many electrons does it have? Plus means it gained or lost electrons. So it lost how many electrons? So it should have, which means the electron configuration for sodium with a +1 charge, 1s2, 2s2, 2p6. By the way, that's also electron configuration for who? How many electrons is that? It is neon's configuration, right? That is neon's configuration. That is neon's configuration. All 3 of those things, oxygen, which is oxide with a -2 charge, sodium ion, and neon, they all have the same electron configuration. That is what is known as being isoelectronic with each other. Something that is isoelectronic has the same electron configuration. By the way, this is also the basis of bonding. What did oxygen do by gaining 2 electrons? It became the same electron configuration as the noble gas. What does sodium do by losing this electron? It backed up to the same electron configuration as a noble gas. Noble gases are chemically inert. They're super stable. It is the basis of all bonding for everybody to end up with the same electron configuration as the noble gases. It's really the basis of all bonding. Why it happens is so that they end up with the same electron configuration as those noble gases. Any questions on that? So if you do have something with a charge, you do need to adjust it. So if I had sulfur, which we looked at before, with a -2 charge, right? That has how many electrons? 18, which means its electron configuration should be 18, right? 1s2, 2s2, 2p6, 3s2, 3p6. 18 is also who on the periodic table? Argon. That is why it has 2 electrons. So it becomes the same electron configuration as argon. So if you have something that has a charge, you need to adjust the electron configuration, add electrons, remove electrons. And if it's a relative representative element, it'll probably end up at noble gas. There's an earlier question about the 4s and the 3d. Transition metals are actually different because of what we just talked about. So if you look at transition metals like iron, which we have there 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. As we talked about before, what happens when it gets filled is that 4s will have the electrons first. Then the 3d will pick up our 6 electrons. But after they get those, there is that switch that occurs. And it's actually the 4s higher in energy than the 3d. And that means when something like iron or a transition metal will go to lose electrons. Say it's iron with a +2 charge. Instead of 26 electrons, it now should have 20. Which one is now the highest electrons? It's actually these. It will lose those s electrons first, and it will lose both of those s electrons first. And the correct configuration here would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, no 4s, are argon, 3d6, yeah, in that case. What happens if iron made a +3 charge? That would be 23 electrons, right? We already know we're going to get rid of these two, right? Where's the next electron come out of? The next highest in energy would be the D. It will come out of there. And it would end up at argon 3d5. So transition metals, if they lose electrons, are different than representative metals. They will always lose these s electrons first. And then if they need, they'll dive into here and take some d electrons out. So that's something a little bit different with transition metals. When they do lose electrons, they will always lose electrons because they are metals in that case. Any questions on things with charges there? All right. We're going to finish this chapter talking about some periodic trends. By the way, that's way fast, that clock, by the way, so you know. All right. So let's talk a little bit about valence electrons. Valence electrons are the outermost highest energy level electrons, and we can find them in our electron configuration. If we look at our nitrogen, 1s2, 2s2, 2p3. These, as we talked about, it's the second energy level, right? Those are the highest energy level. 2 and 3 is 5 valence electrons. The lower energy level electrons are the core electrons. The difference is the valence electrons are not going to be held as tightly, and they are the important electrons in bonding. They're actually the ones that are involved in bonding. The core electrons are closer to the nucleus and held really tight and will not be used in bonding. So it's just those valence electrons. So you could write the electron configuration and figure out the number of valence electrons from the electron configuration, but frankly, who wants to do that? Not me. So there should be an easier way, and there is an easier way. The number of valence electrons will actually equal the group number. So everybody in group 1 has 1 valence electron. Everybody in group number 2 has 2 valence electrons. Everybody in group number 3, 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7, 8 valence electrons. One exception is helium has actually only 2. Why does helium have only 2 valence electrons? How many total electrons does helium have? 2, so it can't have 8. So it is a noble gas, but actually only has 2 electrons total. It only has 2 valence electrons. Everybody else in group 8 has 8 valence electrons as well. So we just did nitrogen. That's group number 5. Group 5 valence electrons. Yeah. Sulfur would have how many valence electrons? Yep. Aluminum would have 3. Right. What about transition metals? Transition metals also equals the group number, but if you remember, we used a representative numbering, which is the A. For those guys, you could just use the regular B numbering, which is basically 1 through 18, basically. And that means that over here, this guy would have 3, 4, 5, 6, 7, 8, 9, 10, and 11, and 12 electrons. So if you have any of those valence electrons for your transition metals, good thing we don't really deal with it too much in here, but it will also equal the group number, the kind of 1 through 18 group number for just the transition metals. And then it kind of goes backwards on that one. Any questions on that? By the way, for electron configuration, there are 2 exceptions to normal electron configuration, and that is chromium, which is 24, and copper, which is 29. If you follow that zigzag back and forth, you will get argon 4s2 3d4, and you will get argon 4s2 3d9. It's been found experimentally for these 2 that actually an extra electron up in the d orbitals actually is more stable. So the correct electron configuration would be argon 4s1 3d5 for chromium, And copper has a very similar one, argon 4s1 3d10. And it's just been found experimentally to be more stable with an extra electron up in the d orbital. They're able to do that because we were just talking about they're very close in energy. So it's not that much energy to get one up there. Those are the two that you're responsible for. Just so you know, if you go underneath copper, underneath chromium on the periodic table, there's a ton of exceptions like silver and stuff like that. For example, palladium here has none in the S. They've all gone up to the D. So there's a lot of exceptions in this area. But for us, chromium and copper, the two that you should be aware of. But in real life, there's a lot more exceptions kind of underneath those guys on the periodic table. So I wanted to mention that. I think I might have not mentioned that. So I just want to do that. Any questions on that there? So as you go down a group on the periodic table, we seem to get more reactive when we talk about metals. So down a group here, lower left of the periodic table. For nonmetals, the most active nonmetal is right here at fluorine, upper right of the periodic table. The reason for that are some periodic trends as to why we see that reactivity occur. So let's talk a little bit about some of these periodic trends. Let's first talk about ionization energy. Ionization energy is the energy that's required to remove an electron from an atom in the gas phase. And the general trend for ionization energy is it increases as you go this way on the periodic table, decreases as you go that way on the periodic table. And metals have low ionization energy and nonmetals have relatively high ionization energy. Electrons actually come off one at a time. So for example, if you look at something like magnesium, the first thing that would happen is magnesium would lose one electron. And that is what's referred to sometimes as the first ionization energy. Then magnesium with a +1 will lose a second electron. That's what is sometimes referred to as the second ionization energy. And maybe this guy with a +2 will then lose one more electron, which will give it a +3 charge. And that would be the third ionization energy. So each of these ionization energies, the energy required to remove one electron. So first is the first electron comes off, second ionization energy is the second one, third is the third, fourth would be the fourth. Do you think it is easier to remove the first electron or the second one? Which one's easier? It is the first one, right? Neutral guy. When you remove the electron, the size of that ion now, is it larger or smaller than what it started with? Smaller, right? Electron cloud shrinks, right? So it becomes smaller. That then moves all the electrons closer to the nucleus, right? Which means they're going to be held tighter. Another get smaller, right? Electrons now closer to that positive charged nucleus, held tighter. Takes more and more energy every time you try to rip off an electron here. So why does something like magnesium only form a +2 charge when it could form a +3 charge? If we look at the electron configuration for magnesium, that is it right there, right? How many valence electrons does that? Magnesium. 2. It says he's right here. So this guy. I lose my second electron. That's all of those guys. Now, what type of electrons am I into at this site when I try to remove the third or the core electron? Close to the nucleus to start with, even closer now because we lost those. Good luck with that. It's probably like a 12-fold factor of energy that you need to try to remove that, and it's probably not going to happen. So that's why we see things like magnesium, for example, will only lose those valence electrons because they're not held as tightly, and that's why it only, for example, a +2 charge, it cannot rip off those core electrons, which are held a lot tighter. Any questions on that there? So that is, again, the general trend in ionization energy. Atomic size, the size of an atom gets smaller as we go to the right and up, and larger as we go down. So another important trend is electron affinity. Electron affinity is the energy change that occurs when we gain an electron. And in terms of electron affinity, it increases as you go this way and decreases as you go this way on the periodic table. And that is not to be confused with electronegativity, which is another important trend. Electronegativity, that is the ability of an atom to attract electrons. Increases as you go this way on the periodic table. Fluorine is the most electronegative element you could have, and decreases as you go down. Those few things, electronegativity, electron affinity, the size of the atom, and ionization energy, is the reason why certain things will gain electrons and certain things will lose electrons. So let's use this as our little diagram here. We have atomic size gets smaller to the right. We'll put in our other stuff. Our ionization energy increases this way, decreases this way. Our maybe not. There we go. Try again. Our electron affinity increases this way, decreases this way. Our electronegativity increases to the right, decreases down. We have our size, and what are we missing there? Electron affinity, ionization energy, size, and electronegativity. These trends all work together for what we see. When we go to the upper right of the periodic table, that's where we find nonmetals. And nonmetals are very small in terms of their size, which means their outer electrons are closer to the nucleus, which means they're held tighter, which means they have very high ionization energy, and they have high electronegativity and high electron affinity, which means they like electrons. All of those trends together tell you that nonmetals like electrons, want to hold on to the electrons they have, and want to take other people's electrons. And that's why what we see with nonmetals is these are the guys typically that will gain electrons because of all of those periodic trends. You go to the opposite end of the periodic table, left and down, that's where we have metals basically, right? Metals have all the trends of they are much larger, which means the outer electrons are further away from the nucleus, not held as tightly. They have very low ionization energy, which means it doesn't take a lot of convincing for them to lose electrons. They have low electron affinity and low electronegativity, which means they're not really interested in gaining electrons. They're pretty much interested in, go ahead, take my electrons. I don't really want any. Go ahead and take them. And that's what we see with metals. Typically are the ones that will lose electrons and become positively charged, while nonmetals will become anions, which are negatively charged because of these. At the extreme of the periodic table, right here at fluorine, this guy is like, I want my electrons, I want your electrons, I'm going to take your electrons. Why? It's most reactive. Non-metal. Down here, bottom left, most reactive metal, because he has all of the properties of take my electrons. I'm not going to hang on to them. Just go ahead and take them, which makes them really, really reactive, right? Willing to give up your electrons pretty easily. Going to make something really reactive. Somebody that wants to grab electrons a lot is going to make it really reactive. And that's why we see the most reactive non-metal upper right, most reactive metal lower left of the periodic table. Any questions on that there? All right. I think that's good. I think that is chapter 4, believe it or not. Yeah. All right, a couple things for you.